Hello everyone, and a very warm welcome to our webinar, ZProtect 5 Power Quality Basic Functionality. In today's webinar, you will first receive an introduction to which power quality disturbances can be measured, logged and reported with the ZProtect 5 protection relay. These functionalities will also be put into context with evaluations widely used in the power quality world. And to complement the theory, an in-depth demonstration of how to parameterize and set up the PQ Basic functionality in a ZProtect 5 protection relay will close the session. My name is Christoph, technical promoter of our CCAM power quality instruments, and I'm very excited to be your moderator during this event. The webinar will, of course, be recorded and made available afterwards, but more details about this at the end of the session. A few words at the start regarding questions which might arise during the webinar. You will not be able to pose your questions to the presenter directly. However, you can post your questions during and after the presentation via the Q&A box located on the top right side of the window. The Q&A widget is accessible once you exit the full screen mode of the presentation. Directly after the webinar, our expert will address your questions during the Q&A session. If we run out of time, questions which we have not yet answered will be answered separately. With these technicalities out of the way, I am very pleased to introduce you our expert of today's webinar, Markus Kraft. Markus, with 30 years of experience at Siemens, is one of our most experienced technical sales specialists who is promoting our solutions in the context of the digital substation, such as the process bus technology, as well as our fault recording portfolio encompassed by the 7KE85. Furthermore, with his years of experience in the research and development of our power quality software, where he started his career, Markus is the ideal promoter for the power quality basic functionality available for the ZProtect 5 protection relays. Markus, welcome to our live event. The stage is yours.
Hello, Christoph. Thank you very much. Yeah, and good morning and good afternoon, everyone out there. In today's webinar, you will learn what kind of power quality disturbances can be measured, logged and reported on using a protection relay. I wish you much success on watching this webinar. And now, before we start, let us take a look on the agenda of today's webinar. At first, I will give you an overview about PQ Basic, means what customer requirements in terms of feeder power quality monitoring are supported and how the results can be reported, or better said, registered. After that, we will have a closer look inside the event interpretation and what's behind the acronyms THT, TDD, and unbalanced monitoring. In Chapter 3, you will learn how to add PQ Basic function blocks as well the mandatory parameterization steps in DIXI 5. Don't be afraid, it is very less parameterization effort. When we have finished the parameterization, I will simulate a voltage dip in the digital twin to show you how comprehensive the power quality basic reporting is. And finally, I will summarize up the customer benefits on using PQ monitoring inside ZProtect 5 protection devices. All right, let me introduce you into the PQ Basic concept first. On the one side, PQ Basic classifies with reference to the measured signals, so-called events. We differentiate three kinds of events. The first is a voltage swell, means as soon as an upper limit is overstepped, the algorithm classifies that as a swell. The second event type is the voltage dip. Here is a lower limit, the indication for the dip classification. And the third one is the voltage interruption, means drops the voltage signal below a parameterized percentage value in relation to the given nominal voltage level. The algorithm classifies that as an interruption. The PQ Basic feature registers for each event type the duration from the beginning to the end, the duration per phase, and per phase the hugest deviation from the limit. As soon as the event is over, a counter will be increased. How that looks like, we will see in the next slide in detail. Additionally, measures PQ Basic so-called mean values, typically 10 million measurements over a longer time range, and registers as soon as a limit is between a defined timestamp, so-called observation period, violated. The following three power quality related distortions can be measured and evaluated in BQ Basic. The THD, or the total harmonic distortion, covers the Waldig harmonics order number 2 up to 20. That THD value is an aggregation of 3000 10-cycle measurements. 10 cycle is at 50 Hz, 200 milliseconds, and 3000 of them represents a 10 minutes aggregation interval. When such interval value exceeds the threshold limit, stores the BQ Basic mechanism the value and some more measurements for detailed reporting. Similar measurement and evaluation are used to monitor limit violations for the total demand distortion, TDD. The main difference to the THD is that the TDD measures the current harmonics and uses different aggregation intervals. The third power quality relevant distortion who needs to be monitored is the unbalance. Here, the evaluation process is slightly different compared to the THD and TDD because voltage unbalanced are measured in 3 seconds average values. These average values will be stored and evaluated over a so-called observation period. At the end of that observation time range, all 3 seconds values comes under consideration, if and how many of them exceeding the upper limit for unbalance. Common for the events and the THD, TDD, and unbalanced monitoring is that as soon as a limit was exceeded, a warning notification will be raised. On the next slide, I will show you different reporting channels. The initial trigger for each kind of reporting mechanism is always a warning. In the middle of the slide is our CBRAK 5 protection relay with firmware higher than 840 displayed. BQ Basic is available for all CBRAK 5 relays, also for compact like 7SX800, as well for the universal relays 7SX82 and 85. Firmware needs to be higher than 840. The first reporting mechanism, I call it notification channel, is the operational log or user log. Let us assume the device has measured a voltage event of type dip. For that, the log covers the timestamp of warning on at the bottom of the list, followed by the information like extreme value per phase, duration of limit violation per phase, as well overall extreme value and overall event duration. Followed by the warning off indicates that the dip counter, in our example, dip number 7. That's the textual description of the event. The next channel shows the graphical visualization of the same event. We attach the 3 event warning indication to the input of an OR logic in a CFC plan. The output of that logic can trigger an external start of the inbuilt protection fault recorder. The result is a COMDRATE file, which covers the phase timeline signals of the event. And below the timeline, we can see binary signals, which indicates the active warning which caused that fault recording. The third channel is IEC 61850 reporting. It offers all kinds of detailed information based on the selected nodes in the IEC 61850 structure during parameterization. And the fourth possibility uses IEC 61850 to route indications to the CCAM PQS or CCAM PAS system. The result is a timestamp list of event type for warning raised and warning cleared. Once more, an overview of all notification channels. To equip or expand a protection relay with power quality basic functionality requires no changes on hardware. Depending on the monitoring functionality which is needed on the feeder, a specific amount of function points are required. The THD is already included in the CBRAK 5 protection relay. In the case the unbalance should be monitored, we have to install 20 function points. And for event classification of dip, swell, and interruption, we need 10 function points. For each of them means in sum 30 function points. And finally, the TDD, the current harmonics, can be evaluated with additionally 10 function points. Just to remember once more, BQBasic supports the analysis of THT up to the 20th voltage harmonic, further the TDD, the level of current harmonics compared to the previous interval, and unbalanced considering a static observation interval. On the right side, we can see the 3 event types of dip, swell, and interruption. In my opinion, it is important that you be aware that what kind of customer requirements are not covered in BQBasic. That's a so-called grid code evaluation conform to EN 5160. That grid code requests to measure and evaluate the following characteristics. So voltage min and max, the individual limits for the 25 voltage harmonics, the main signaling, the frequency min and max limit, the long-term flicker PLD, and for each event a classification for short and long, depending on the event duration. These characteristics, measurement and evaluation are fully implemented in the products CCAM Q100 and CCAM Q200, our so-called power quality recorder with Class A accuracy of 0.1%. So let us proceed to the next chapter of the webinar. In that chapter, you will learn how to interpret the BQBasic evaluation results properly. Let us start with a graphic on the right side down. We can see the timeline signal and on the y-axis the voltage in percent. 100% represents the nominal voltage level. Let us assume in our example 230 kV. Drops now the voltage signal below the 90% line, means below 207 kV, a voltage dip event is detected. The event starts on crossing the 90% limit line downwards. A parameter called dropout differential comes under consideration to avoid having a permanently retrigger of the event when the signal is nearby the limit line. By the way, that parameter is in power quality bonnet terminology named hysteresis. So the dropout differential needs to be overstepped to finalize the event. In our example, 90% plus 2% dropout. When the signal crosses the 92 limit line upwards, it recovers the above 211 kV. Now that limit line crossing finalizes the event. Above the timeline graphics are the possible parameters for voltage dip displayed. We have the threshold, typically 90% for nominal voltage, the dropout differential, and a possible delay of the warning indication in seconds. The voltage swell follows the same algorithm and warning procedure. The only difference is that the swell event starts with 100% above nominal and ends when the signal drops below 110 minus 2. Dropout differential means 108% in our example when the voltage level recovers below 248 kV. And the voltage event type interruption has a predefined threshold of 5%. It starts as soon as the voltage drops below 11.5 kV and ends when the voltage signal rises above 16 kV. 5% limit plus dropout differential of 2%. Common for all 3 event types is a detailed event evaluation, means the duration for each single phase in measured and written in the user log. The extreme lowest or highest deviation for each separate phase communicated it to the user log. An overall duration means when the signal of the first phase drops below the limit and the last phase recovers above the limit, represents the so-called overall duration. Okay, that's so far for the event detection in BQBasic. Let us move to the disturbances THT, TDD, and unbalance. From power quality perspective, the total harmonic distortion is an important quality criterion. In the graphic on the right side down, you can see how a sinus shape looks like when the harmonic level is too high. The result could be that electrical infrastructure is sporadically producing malfunctions like reset or overheating of equipment. The formula for the THD you can see on the left. In PQBasic, it summarizes the voltage harmonics from order number 2 up to 20. The 20s, for example, the frequency of the 20s harmonics is 20 times 50 Hz equals 1 kHz. That summary will be divided with the voltage amplitude of the 50 Hz fundamental wave. The measured interval of the THD is not half cycle like for the events. The THD comes a so-called aggregation interval under consideration. Aggregation means that a 10-minute average value will be aggregated of 3,000ths of 10 cycles RMS values. That 10 minutes value will be checked if the parameterized threshold is exceeded. If yes, a warning will be notified and selected for each phase. The highest THD value are registered and labeled as a so-called THD abnormal. In parallel, for statistical purpose, the worst 3-second THD value will be long-term stored in the device memory. It's called THD VPH max. This statistical value can be manually reset using the device front panel or via binary signal or communication protocol and using the Dixie Online access. On the next slide, the total demand distortion will be described. From evaluation perspective, the TDD will be handled like the THD. When an average value exceeds the threshold value, a warning will be generated and the violated value are logged as TDD abnormal. So possible intervals at THD were 1 or 10 minutes. At TDD, the interval can be set to 15 or 30 minutes. The calculation is slightly different. The first difference is that the TDD checks the number of current harmonics, and the calculation refers to the harmonic level from previous measurement interval. You remember, the THD is the ratio to the fundamental 50 Hz voltage signal. Due to the current is dynamically, therefore, the ratio will be calculated of the maximum demand load current. The statistical 3-second TDD max value are stored and can be reset like I explained at the THD. Let us go forward to the last characteristics, what can be measured and evaluated with PQBasic, the voltage unbalanced, also called asymmetry. The unbalanced monitoring supports 0 to positive sequence systems and negative to positive sequence systems. The parameter threshold is the maximum allowed unbalance. The dropout ratio works as hysteresis to avoid a permanently retrigger of the warning. The next 3 parameters in the dialogues are needed for a long time period evaluation procedure. We need that kind of parameters because at unbalanced running 2 different evaluation processes in parallel. For better understanding of the following explanations, I named the evaluation processes as follows. The upper one fires a warning triggered by an operation and value threshold violation. And the lower and gives a warning after a dedicated observation period is gone. That could be 1 day or a complete week. We will take a closer look on those parameters some slides later. On the next slide, I will show you will learn also how operational limits evaluated and processed in this context. Let us begin with the operational limit. It checks the actual 3-second average value against the threshold. As soon as the limit is overstepped, a warning will be fired, and the following 3 evaluation details are logged. the violated 3 seconds average value, which was a trigger for the new locking, the latest 10-minute average value, and the last 0.2 seconds maximum value in between the previous 10 minutes. And in the case this 0.2 seconds maximum value is higher than the last statistical long-term stored measurement, the max overall will be updated with the new worst measurement. That overall register can be reset like we know from THD and TDD via menu on the front panel or binary signal, communication command, and in Dixie Online Access. And the second workflow consists of an observation period of a single day or a complete week. The period limit evaluation calculates for the previous observation interval the rate of 10-minute values which have not exceeded the limit. The result in the screenshot shows that all the 10-minute average values are below the thresholds. Therefore, the qualification rate is 100%. The highest 0.2 second average value independent from the threshold, and a so-called percentile value. I would like to explain that calculation on a separate slide. Our parameterized observation interval is, for example, 1 day. 1 day equals 24 hours. 24 hours equals 144 10-minute average values. Next step is to sort those 144 values from the lowest to the highest, as we can see in the diagram below. Now we need to get 95% of them. When 144 is 100% equals 137, 95% of them. That means we need to know the unbalanced value of measurement number 137. The value number 137 has a percentile value of 0.85%. That's uncritical because the threshold was parameterized with 2%. In the case the 137th value is exceeding the threshold, then a warning will be fired, and in the user log, the max value, the percentile value, and the qualification rates are reported with a suffix abnormal. Okay, that was from the BQ Basic details, the last and the most powerful functionality from the evaluation, as well from result reporting point of view. The following chapter, I will introduce you how to parameterize BQ Basic. In our example today, we are using an overcurrent protection relay of type 7SJ85. The parameterization workflow will be done in 3 mandatory steps and 1 optional. When side by side to the textual user log information, also a graphical image of the event is required. Therefore, we have the option to trigger a Comtrade file. First, we must expand the function group voltage current 3-phase with the BQ Basic function blocks. From Dixie library, we must drag and drop the function blocks TDD, THD, voltage unbalanced, and the voltage variation, which covers the 3 events. Just for information, BQ Basic is available for all Simbric 5 relays and the compact like 7SX800, as well for the universal relays 7SX82 and 85. We need firmware higher than 840. Sure, and like we have seen at the beginning, 60 function points to activate all these BQ features. The only device which is not implementing BQ Basic is a Vault recorder 7Key85, because the 7Key85 has already more comprehensive measurement method implemented. Now let us take a look on the default settings for the voltage event, dip, swell, and interruption. We can see that the dip is predefined with 90% of nominal voltage, the swell with 110%, and the interruption will be detected when the voltage signal drops below 5%. Unfortunately, the default mode is off. Do not forget to change the settings for each event type to on. I will use the same chronology like in the functional description of the chapter before. That means we will proceed with a THD setting. The mandatory parameter for the THD is the threshold value. When that value is exceeded, the warning and logging mechanism starts up. The aggregation interval can be parameterized for 1 and 10 minutes. The predefined 10 minutes is a typical power quality settings. Oh, that's also far for the THD. The only difference between the THD and the TDD is that we define the length of an interval to compare the measured values from them with the actual interval. All right, and now the unbalance. In the function voltage unbalance, the following stages are available. Ratio of the negative sequence voltage to the positive sequence voltage and ratio of the zero sequence voltage to the positive sequence voltage. The parameters starts with a mode that needs to be changed to on when you want to monitor voltage unbalance. With the parameter threshold, you set the threshold value to define the degree of voltage unbalance which is not considered as normal anymore. In the average value, if this average value exceeds the threshold value, a voltage unbalance is detected and the indication warning is generated. With the parameter dropout ratio, you set the dropout ratio for the voltage unbalanced. If the average value is smaller than the result of the threshold value multiplied by the dropout ratio, the indication warning for the voltage unbalance disappears. With the parameter observation period, you set the period of the observation. The observation is executed and repeatedly weekly according to the start day, specified by the parameter starting day of week. When you choose daily, the observation is executed and repeated every day. The last parameter in the dialog is a percentile. The default setting is 95 according to the standard EN 5160, means 95% of the 10-minute average values are smaller to the percentile value in the last observation period. You remember, a warning will be fired when the percentile value is above the threshold. And do not forget the parameter in the general section on the top. The calculation in the stage starts only when the voltage of positive sequence exceeds that minimum. We learned now as soon as a threshold are exceeded, a warning will be notified, and a lot of evaluation results are reported by these functions. Let us together take a look into the information routing of DXY5 to see how the evaluation results can be routed into the user logs. On the top, we can see the column of the user log. I've already added or routed a lot of information related to a voltage dip. On the left side, we can see what's provided in detail by the evaluation. It starts on the top with a warning indication, followed by the duration overall, when the first phase crosses a limit till the last phase recovers to normal. And after that, the phase to ground related, or like in the screenshot, the phase-to-phase related duration can be routed into the user log. The next information is the voltage residual, means voltage residual that is the worst measured value during this event. The extreme value for separate phase listed below. And finally, the counter voltage value will be increased by each new detected voltage dip. Equally amount of information are provided for voltage swell and voltage interruption on the bottom and on the right side of the screenshot. For the THD, the total harmonic distortion, it allows the routing matrix only two kind of informations. However, that information covers combined results data. That means the warning on includes the affected phases, and the THD voltage phase abnormal includes the extreme value per phase. Absolutely similar is the routing possibilities for the total demand distortion. At the unbalance, we can find at the beginning the warning for the 3 seconds operational limit value, and some rows below, the percentile warning. You can remember the percentile warning will be fired when the observation period of 1 day or 1 week is finished. Only abnormal measured values will be provided for routing to the user logs, like qualification rate abnormal, percentile value abnormal, and maximum value during observation period abnormal. To get familiar with all those acronyms, I recommend you take a look into our Power Quality Basic chapter of all our dedicated device manuals. Till now, we have seen the evaluation results in textual or numeric style. When you want to also have a graphical report of an event, you can trigger the internal protection fault recorder of your relay. I will explain how to parameterize such CFC trigger logic. Such CFC logic is quite easy to implement. What we have to do is to drag and drop an OR logic block from the library into the CFC chart area, displayed on the left side. Select this OR logic and remove the check marks on the third invisible checkbox because by default only 2 inputs are visible. Okay, and now we can drag and drop from the signal catalog the warnings of dip, swell, and interruption to the inputs X1, X2, X3 on the left side of the logic block, and the external start command of the protection fault recorder to the output Y on the right side of the logic block. That's all. As soon as a warning becomes now active, a complete fault record will be started. Before we test that stuff with a digital twin, I would like to show you how, for better understanding, an analyzed fault record with reference to the results reporting in IEC 61850. We can see a fault record and the voltage signals dropping down and rising upwards. Below the timeline, I have added the binary tracks for the 3 warning signals for dip, swell, and interruption. In that now appearing screenshot is the IEC 61850 reporting displayed. Let us now together compare that graphical and the textual voltage dip evaluation results. The blue cursor in the middle provides the extreme value of the voltage dip. In the example, 179.98 kilovolt. Okay. That measurement in ratio to the nominal voltage level of 230 kV equals 77.9%. Exactly that results can be seen in the IEC 61850 structure SMX measurement, instantaneous magnitudes. Let us now check the duration of the voltage dip. The length of the binary track is the time between warning on and warning off. In our scenario, 1079 milliseconds. Although that evaluation result fits one-to-one to the information in the IEC 61850 reporting. Before we go into a short break, let me explain how to test a voltage dip on using the digital twin. What applications are running on my system for testing the whole workflow? First, DXY5 for parameterization and exporting the simulation file for the digital twin, and exporting the IID file, the device description for integration into a CCAM PQS. The digital twin to visualize or virtualize the device and simulate the measurement inputs, the CCAM PQS, which uploads the CFC triggered fault record in contract format. The file will be stored into the CCAM PQS archive. As soon as the fault record is stored in the archive, it will be listed in the HMI of the CCAM PQ analyzer. And additionally, a possibility is to access the data of the device on using the so-called Web UI. Okay, let us now have a break of 10 minutes. After the break, I will proceed with the live parameterization of the relay and the test using the digital twin. Thank you very much. See you later.
Welcome back. I hope you enjoyed the break and you took your time to grab a drink. You probably saw us grabbing a drink as well, a bit of refreshment. That was an interesting start to the session. Thank you for sticking around. And I mean, this is going to be the special part. You will see a demonstration by Marcus again. So nothing more from me. Marcus, your turn again.
All right.
Thanks again.
Yeah.
Have fun.
Thank you, Christoph. All right. So once more, and short overview for the practical session with DIXI, Digital Twin, CECAM PQS, PQ Analyzer, and Web UI. We can see here the components. We will parameterize the device in DIXI, activate the Digital Twin, upload the simulation file, connect the CECAM PQS system and the CECAM PQ Analyzer. And in the Digital Twin, we will afterwards changing the limits of the voltage input, simulate a so-called voltage dip or swell, an event. Let us see how the device is reacting, the virtual device is reacting, and the upload of the COM files of fault recording with the CECAM PQS and the visualization in the CECAM PQ Analyzer. Okay, and now we switch to my laptop to the DIXI application. All right, here we can see DIXI 5 Premium, and it's an MD project. The first step, what we have to do is we will add a device into our project. On double-clicking on this node, we can add here, we have two possibilities, either we add here in short code or in product code and long code, or we configure our device manually. And this is a way what we want to do now. I click on configure, and this is an old one. We will choose a new one, go in the CBRIC 5 area, select the overcurrent protection 7SJ85 relay, and in our scenario, a 4 current 4 voltage transformer device. Drag and drop. So now we have to select or have to define the voltage level, the power supply, the variant. If it's an AC DC device or only a DC device, let us choose this one. Next one is, do we need to have function points or classes? Yes, sure. As I have explained, we need function points because in some, when we are activate all PQ features, PQ basic features, we need 60. And when you have only the events, 30 function points are sufficient. This means let us set here 100 or 75, does not matter. How does an integrated Ethernet port J looks like? For that, we want to have IEC61850 on board, inclusive Goose, because with the IEC61850, we will do the communication between the device and the CECAM PQS afterwards. And from the application template perspective, let us select here the first one for voltage for current and simple over current relay. All right. After a couple of seconds, the device will appear. It will be now generated in the background with the hardware parameterization, what we have already just defined. The next step will be that, and this is a very important step from my point of view, to give the device a good name, to make it clear what is the feeder name, what will be monitored, where is the device located, where is it installed. So here now a new 7SJ85 appears. First of all, we go in the device information. I do a double click on that and give the device a good name. All right, so Siemens Promenade. I hope I did no typing mismatch. Did I? No, perfect. Copy, and we will also add this name into the IEC61850 name. All right, good. The next step will be, we have to care about how the device looks like from the hardware point of view. This means we have to add an CD and current transformer. Let us select one from the catalog. terminals. We have a modular device, and we will choose 4 current CTs. Drag and drop. So the next step is, because we want to connect the device to a CCAM PQS system, we have to parameterize our port J Ethernet interface. We have to change here the default IP address to a valid number. In our case, we will choose 192.168.2.14, for example. 2.14. All right. And we may not forget to activate in the communication the IEC 650 communication protocol. All right. How does the front panel looks like? It's still empty here, because we can decide now what kind of operation panel should be used. I would like to have here a large display with dual color LED. Perfect, because there we have more space on the display to visualize a lot of event information or measurements. Okay, so, and the next step is essential, what I've already explained is a theoretical part. We have to expand the function group voltage current 3-phase by our power quality function blocks. Here on the left is a function group voltage current 3-phase number 1. And right now only protection, typically function blocks available by default. What we have to add now, we have to go in the library, Global Dixie library, types, go to the overcurrent protection relays, the 7SJ85. Here inside the function group voltage current 3-phase. Inside these function groups, we can find the power quality basic chapter. And here are the evaluation mechanism for TDD, THD, voltage unbalanced, and voltage variation. Voltage variation covers the 3 events, dip, swell, and interruption. So these function blocks need now to be dragged and dropped from this library into our function group voltage current 3-phase. I drag it from here and drop it there. TDD is on board. Next is the THD, the total harmonic distortion. Drag and drop. For the THD, we have to add a stage for current. And the third one is a voltage unbalance. Drag and drop it here. All right. And the last but not least, our voltage variation function block. Drag and drop it inside the function group voltage current 3-phase. So, and now we can consider on parameterizing or adjust the settings in these PQ basic functionalities. First of all, let us go to the voltage variation. I do a double click on that here on the left hand side in the tree. And then we can see in the middle, removing these matching numbers, the 3 events, the dip, the swell, and the interruption. The measured value type is phase to phase. Let me switch it phase to ground. So, and what I would like to do is I would like to rename the default names of these events to make it more clear, to make it already clear inside the name what is the threshold for these kind of events. This means we will define now a dip assign it with 90%, as well with 110, and then an interruption with 5%. For that, to rename this event name, we have to go in the properties window here on the bottom, in the settings, and then I can change in the names in the details. So, and we say the first one should be named as dip below 90%, for example. Oh, caps lock. Horrible. below 90%. Return. Now the tip is renamed. Okay, next one for the swell. Same procedure. We say this, it's a swell and it's above 110%. And last one, the interruption. I'm doing this assignment because we can have more stages, and the stages can have individual settings. It could also be I want to have a swell when the voltage becomes above 105% only. Yeah? So, and the interruption, it's below 5%. So this is now for the naming, and now let us care about the setting. We start once more with a dip. So the default, as I've explained, all these events are switched off, deactivated. Do not forget to keep it on. Yeah? And the default setting, the threshold, is already 90. 90 is a very, very familiar, typically settings from the power quality perspective. As I said also, the swell with 110% above the nominal, a very common setting. I don't like to change it here. Yeah, the dropout differential, what we are in the power quality context very often call hysteresis, is per default 2%. When this event warning will be fired too often because the signal what will be measured is, how to say, too nervous, that you can increase this dropout differential to don't have too many events fired or warnings fired. So the swell above 110, switch it on. And also the interruption below 5%, we have to switch on. This means we can one-to-one use the default settings. Let us now take a look on the unbalanced. I do a double click here in the tree. It also needs to be switched on because we have just added it from the library. The default ratio of negative sequence voltage view 2 and the positive sequence for voltage view 1. Here's the threshold 2%, also a very common setting, and the dropout ratio 0.9%. The observation is here by default weekly and it starts on Sunday. You can change this also when you have an shorter evaluation time for these for the unbalance or asymmetry. You can switch it to day, and then you get an every day in evaluation results. Yeah, this means the warning indication will be fired quite more early. Yeah, but typically it's also from the power quality perspective a time range which is quite common. We will find this observation week or monitoring week or evaluation week also in the grid code EN 5160, for example. Okay, we keep it in weekly. And let us now jump to the next one, to the total harmonic distortion, or the THT. Here is the voltage total harmonic distortion already on, and the aggregation interval is 10 minutes, quite okay. And the threshold is 8%. This means when the THT, and the THT in PQ Basic is the calculation based on the second harmonic up to the 20th harmonics. This means up to 1 kilohertz. This is a difference that we compare with the power quality recorders. They are doing the DHT up to the harmonic number 40. Yeah. But we can also give a statement here if the total harmonic distortion, this means the harmonic voltage level is too high when from the second to the 20th one, the threshold increases above 8%. Okay. Next one is a TDD, is a total demand distortion. And this also needs to switch on. And here's the threshold by default 5%. Okay, so let us now go to the information routing matrix, because we have now parameterized the thresholds for these functionalities. What we now want to do, we are routing or mapping these evaluation results from the dedicated characteristics into a user log or into a fault log. Okay, for that we go in the information routing matrix. Yeah, it reminds us we have to synchronize the hardware. Let us do this because we have done a lot of changes for CTs and the front panel. All right, successfully done. Good. To make this view a little bit more common, let me move out here the project tree and make this a little bit more compact. Okay, so this is now the information routing matrix. Where are our dips, swell, and interruptions? We can find it in the function group voltage current three-phase. Scroll down, here are the voltage variations. And now you can see for us, it's easy to find, to detect, this is exactly the event what I'm looking for. Because here you can see now the naming what we have given before in the parameterization of the dedicated event. Give it a good name, make it life easier. Okay, we will expand the dip. And what information can now be routed into a so-called user log. Here is a user log, for example. And each cell or field which is light gray, we can add an X that the information will be routed. I think the mandatory one is the warning itself. When the limit is overstepped, a warning will be fired. This information, I would like to have it in the user log, documented. I can add the duration overall, but also the duration phase-wise is possible. As the same procedure for the residual voltage, the lowest voltage inside the complete event from the beginning to the end, or the single phase voltages when they are increasing separately, decreasing separately. So I would like to have the overall duration, it's okay for me, and the worst value here for the residual voltage. So, all right, I would like also give this warning here a dedicated name. We call it here in Dixie an alternative name. This I'm doing because I want to route these warning signals for the dip, for the swell, and for the interruption also inside the protection fault recorder as a binary track. Because later on we will create the CFC logic with the 3 inputs for dip, swell, interruption warning, and the output of this OR logic will be an external trigger for the protection fault recorder. And when this complete file is generated, I need to know what was the trigger for this fault record, and therefore we will map these warning signals as binary track inside the COMTRADE. And to have a good name already also there, or in short name, I don't want to see the complete tree here on the left-hand side. I choose here an alternative name for that. So this means the alternative name is nearly equal like we did already for the event. We are here in the dip. This means dip. Kleiner 90%. Perfect. And do not forget to map it here into the so-called protection fault recorder. On editing and X for routed. So this now, when the complete file are done, this indication with this name are mapped as a binary track inside the fault record. And the same procedure we will do now for the swell. Here is a swell. Swell higher than 110%. Return inside the fault recorder. And sure, also I need this information in my user log here. The warning, the overall duration, and the few SV means the extreme swell voltage. So, and last but not least, what I would like to show you, the interruption, so warning for interruption. No, I think it's too long. Interrupt below 5%. Typing mismatch. Good. We map it in the fault recorder. We map this information in the user log. And also, how long has this interruption taken on dropping below 5% and recovering above this 5% plus 2% hysteresis was the lowest voltage level inside the event or during the event. And I've forgotten something, the counter, also very important information. I would like to have the counter in my log, because when we do in long-term monitoring of a feeder, for example, in a week or a month or a quarter, a year, for example, it's good to know in the log afterwards how many voltage diff have been fetched or analyzed detected inside this observation time range over, for example, 1 year. Yeah, and have a clear statement. In this year, we had recognized 5 voltage dips, and the extreme value was this one, and the duration of the longest duration is that kind of seconds, milliseconds, or whatever. Okay, do not forget to add the counter information also to here, and also the counter for the voltage dip. Okay, good. So, to see also on the front panel of the device that an event was detected, let us now assign these warning indications to the LEDs of the device. For that, we go to the chapter destination, open the LEDs, and it's more or less the same procedure. The voltage dip, warning. Let us take on the LED number 2. The voltage swell warning, we will choose to the LED number 3. And the interruption warning on the LED number 4. And do not wonder why I have not done the LED number 1. The LED number 1, I would like to indicate to the operator, to the user, that fault records are started. And for that, we will go in the chapter recording, fault recorder, control, and we will map our external start to the LED number 1. All right. Right, this was the wrong one. External start, unlatched. Okay, so to get now this external start really activated means we will now together design a small CFC logic with an OR and logic block. The inputs for this OR are these 3 warnings, yeah, and the output will be a signal to this protection fault recorder. Okay, we go back to the project tree. Here we are. Go in the chapter charts, CFC, add a new chart. All right. So now we are in the chart area. What we need to add a logical block of type OR, drag and drop. And this is what I said in the presentation chat before, in the theoretical part. By default, the OR logic comes around with 2 inputs, yeah, and we need 3. No, we need a dip swell and interruption warning. To get the 3rd input, you have to select the logic block, go in the properties chapter, select the interface, and you have to remove this check mark for invisible. When we remove that, we can see, now we have 3. Perfect. Good. And now it's quite easy. We go to the signals, catalog, voltage current 3-phase number 1, voltage variations, dip below 90, and this warning I will assign to the input number X1. Go to the swell, drag and drop the warning, and last but not least, the interruption warning as the OR logic input number 3. So, and when at least one of these warnings are appearing or becoming active, I would like to start in the recording chapter, the protection fault recorder, as an external start, drag and drop. Perfect. All right. So when now an warning becomes active, this one or this one or this one, the internal fault recorder will be started. And as we have seen, we have already routed with an X our warning binary tracks. And I know that inside the complete file of a protection relay, a lot of binary tracks are already predefined. Yeah? And to make our new binary tracks a little bit more important, we have to go now to once more to the project tree and to the recorder and keep our additionally 3 binary tracks in the signal order in the SPS on the top of the list. No? It's here somewhere in between, no? The below 90, 110, and 5%. Let us move these upwards at the beginning of the list of the binary tracks. Okay, perfect. So all logic is done. We have the LEDs assigned. The naming of the LEDs by default, I think this is also not very good. Let us check how does this looks like. We select the device front panel and check here how this naming of the LEDs. Okay, it covers our name. This is good, but external start, I name it here PFR start. This means PFR, protection fault recorder started. So, all right. So the next step is we export now this device on selecting the device with a right click in the export dialog, a so-called simulation file, SEM, SIM file, and this SIM file is the import file for the digital twin. Yeah? This simulation file covers now the complete device functionality plus look and feel, all the hardware, constellation, whatever. Yeah? The complete device will be exported in a SIM. The SIM will be imported into the digital twin, and then we are able to visualize the device. And a second information what needs to be exported also in this dialog is a so-called IID file, instantiated IID description, also based on IEC 61850. And this IID file we need afterwards to import it into our substation automation system, the CCAM PQS. Yeah? And then the communication takes place between the virtual device, the CCAM PQS, and the CCAM PQ analyzer for visualization of such a fault record. So then let us do that. I've done it already in the background. This means we have here the digital twin. Our device is already, I will show you how to export it. You go to the project button, and here on the right-hand side on the top is an SIM Plus icon. Here you can select the simulation file, that it will be imported to the twin. Here's the device, and you can select it, click on the orange button for start simulation. And then is here our virtual 7SJ85 with our BQ basic settings or parameterization. All right, let me zoom in a little bit to make it more clear what's going on here on the front panel. We can see here is the LED number 1 is assigned to the PFR start, means a protection fault recorder, the internal fault recorder mechanism. LED number 2 appears when an dip was indicated, 3 and swell, and the 4th one here with an interruption. On this input field, I can simulate now voltage in the digital twin. I select now this dedicated field and drop down the voltage with a cursor down button. And when we are below a dedicated 90% limit, then you will see that the dip indication LED goes on and the protection fault recorder. Protection fault recorder as a result of our done CFC logic. Here we are. No? Dip indication was detected. I increased the voltage once more back to nominal. This means the dip was over. The protection fault record was done. Same procedure we can test with a voltage swell. So LED number 3, when I'm increasing now the voltage, swell indications are done, protection for the record are started. Good. And when we switch off the injection completely, zack, interruption. And this indication takes as long as the interruption takes. Yeah? And when I switch on once more the voltage, then it recovers 75. Otherwise, tip will be detected. Perfect. So this means the functional test of the relay based on our parameterization, what we have done, looks like good. No? This means all the 3 events will be detected, classified, notified on the front panel. And now let us take a look. How does this looks like in the CCAM PQS? For that, let us chart out the CCAM PQS system. Here we can see now a CCAM PQS system with an archive, a 61850 communication protocol, and an interface. To integrate now D7SJ85 into our CCAM PQS, we have to import on this interface node the IID file. Here we are. So port J, all right, let's import. So now the device IID file will be imported, interpreted, and when this is successfully finished, then the device appears here below our interface node. And when this is finished, we will care about design a little bit of topology and assign this device also to a topology node. To make it clear afterwards in the CCAM PQ analyzer from what device inside the topology, when we have more devices, the forward record comes from. Here is now our protection relay. It covers the name, it covers the IP address, perfect. I have to activate the forward record transmission to get the COM transferred. And in the topology tree, I've defined here an example topology, region Franconia, station Siemens campus, voltage level 11 kV, and the feeder is a e-car chargers 0.1 to 30. This is, by the way, really physical here available, not far away from this building. It's a parking house, and the lowest areas are only for e-cars, and there's a substation integrated in this house or in this building. So here is the node. I select now the CCAM node on the top and dragging and dropping or drag and drop the so-called upper value of our PQ basic device. For that, let me filter on that. Upper, here we are, OPR. I drag and drop this to this node. Perfect. All right. So, and now we have to go to UI operation, and they update view. And after that, we can say update system. So, and now our new imported device will be integrated in this CCAM PQS runtime, and it will connect, it tries to connect the virtual device inside the digital twin. And when this communication is successfully done, then we can see that all indications here on the left-hand side in the topology tree becoming green. First of all, they are becoming purple, and then they are becoming green. So successfully done, no warnings. System is online, the archive is online, and now the communication driver wants to contact or connect, go online to the physical device inside the digital twin. Here we are. So this means we have now a runtime system, CCAM PQS, connected to a virtual device inside the digital twin. Perfect. So next step, you can remember the slide what I showed you just before and after the break. We have Dixie as a parameterization, twin virtualize the device. CCAM-PQS connect to the virtual device. This step is now done successfully. And now we have to activate CCAM-PQ Analyzer, because we want to visualize in the CCAM-PQ Analyzer also the fault records. Today is the 8th March. Here already some fault records appeared or arrived. We have now right now 5 in the queue. Let me close a couple of windows here to see online how it's going on changing the value in the twin and see the result in the CCAM-PQ Analyzer. So, okay, tricky. I have to change the resolution. Okay, so right now we have 5 fault records in the analyzer visible in our substation automation system. I will now decrease once more the voltage to indicate a dip. Here we are, recovering back. Protection fault recorder was done, and as soon as this fault record is finished, because the device is connected via IEC61850 to the CCAM-PQS, the device sends an indication, a record made to the runtime system, to the CCAM-PQS. And when this record made is fetched from the CCAM-PQS, it will upload the fault record into the archive of the CCAM-PQS and show it in the CCAM-PQ Analyzer view. And here is a number 6. This is what we have just triggered. I do a double click on this fault record, and now we can see the COMT rate. Let me move from the instantaneous to the RMS value. And here is the decreasing voltage signal, what I have simulated in the twin. And the indication is, this is a big benefit on using these binary tracks for these 3 kind of warnings. On the top of the list, we can see, it was a dip. It was from here to here. Yeah, this means it went down below 90% of nominal, and here it recovers above 92% of nominal. Perfect. When we are doing this measurement of this voltage dip, how long has it taken from the beginning to the end? It's the same like we are communicated in the IEC61850 reporting engine. Okay, so far. Let us take a look on, and this is now in the, when you remember the PowerPoint on the left-hand side, the web UI of this device. We can also call the web UI connecting the device. And this is now the web UI of our 7SJ85 PQ Basic feeder. And here we can also take a look on these records. In the recording chapter, fault recorder, have you seen it? 6 records. This is more or less exactly what we have also in our CCAM-PQS and here in the CCAM-PQ Analyzer Incident Explorer visible. The last one was this one. Here we are. We can export these records into the file system, but we can also visualize the record here in this web UI. It loads now the timelines here below, phase-wise, and here you can see what's going on here with the voltage, and also here the binary channels or binary tracks are visible. It was a dip, and the issue was it went below 90%. All right. That's so far from the practical stuff. We have done now the parameterization. We have done a test on using the digital twin. We visualize the results via in a substation automation system and in the CCAM-PQ Analyzer. We have done the visualization of the web UI. All right. Let me now summarize before we come to the end. Okay, PQ Basic supports for TSOs as well for DSOs on monitoring feeder in terms of power quality. The functionality detects power quality distortions, logs, and reports evaluation results and counts for statistical purpose events. Can we see the correct page? Yeah, all right. It notifies a so-called warning using IEC 61850 reporting, for example, to control centers. Yeah,
Ja. Hier haben wir das so. Aber das ist den Ton natürlich nicht, ne?
Doch.
Na, doch.
Aber den Ton könnt ihr eigentlich rein. Nee, ich komme nicht rein.
Gerhard,
That's right.
can you hear us? Yes.
Yeah.
Okay, good.
Well,
All right.
this is live.
Yeah.
Quick look out of the studio. We're still having some problems. You have to be back in a few seconds.
Yeah.
But
Yeah, from
well,
the
that's
presentation perspective or from the live demo, everything worked well. And in just this moment where we are able to switch back to the power and some equipment in the infrastructure is passing away. Let me summarize the benefits for DSOs and distribution companies or customers. Yeah, PQ Basic supports to monitor feeders in terms of power quality. That's clear, no? The functionality text. The functionality detects power quality distortions, logs, and reports evaluation results and counts for statistical purpose events. It notifies so-called warning using IEC 61750 reportings, for example, to control centers. A fault record can be triggered, what we have in parallel to the textual log information. The measurement and the evaluation of total harmonic distortion as well as the total demand distortion provides a clear picture about the harmonic level at critical load situation. And very important, there is no change of hardware necessary to activate the PQ Basic functions in an installed protection relay in the field, for example. The already predefined function blocks can be simply dragged and dropped from Dixie library. So, and now I'm at the end of the presentation. I hope you enjoyed the webinar also with these short technical problems here in the infrastructure of the studio. And yeah, Christoph, do we have questions already?
we do have some, but
All right, then let us try to answer them. Yeah.
Let me just first of all thank you, Marcus, for the presentation. Thank you for the great in-depth demonstration and everything you told us about PQ Basic.
All right.
A few words that I want to summarize as well. First thing, PQ Basic is probably the best thing that you can do as a first step for power quality measurements. It's easily implemented in every Ciprotec 5 protection relay. And especially, it doesn't matter if it's brownfield or greenfield, there are no hardware changes required. The only requirement is the firmware, which has to be above 8.40. One more thing, the option to easily capture voltage events as a COMTRADE file with a Ciprotec 5 protection relay can significantly improve your knowledge of the happenings in your energy grid. And the integration of these features in the control center via the communication protocol IEC 61850 also provides great accessibility. But what I want again to especially highlight is the practical insight you gave us into parameterization of the PQ Basic functionalities you offered us with the help of the digital twin, which apparently worked, and luckily the system went down after that. And let's just take a couple more minutes. I'll pick about 5 minutes because we're already over the time to get some questions in. I would remind you about the question box in the top right corner of your screen. Just type them in, but we already have quite a lot of them. So
and all that we are not able to answer because of the time right now and the issues in the hardware issues in the background, you will get an email with all questions will be answered, and it will be distributed as a complete audience with have been joined today.
Yeah. So I have to drop us down. Sorry, hand and everything, but let me try to remove some of them. Yeah, okay. The lighting is bad. this is not going to change. So one first question. There was a question about what type of material can be distributed or read to have some more knowledge about the training. I think Gerd already told us that we have already put the presentation slides in the must be somewhere below the chat. Again, same side. And on the Ciprotec 5 manuals, there is an individual chapter already for the PQ Basic functionalities, and it should be chapter 11.
It depends on the relay type, but there's a dedicated PQ Basic chapter in each manual of the relay types.
So-
Yeah.
If you take a look at the manual, everything with version 8.40 and above
Mhm.
is already there. There was one question about if PQ Basic is standard for each and every 65 protection relay. So, and especially if it's also the case for 7SJ82,
Mhm.
or if it's an add-on that you have to pick up during the ordering of the relay.
Yeah, there's, as I said, no hardware additionally necessary to have PQ Basic in the relay. You need, when you have the full range of unbalanced DHT, TDD, and the 3 events, you have to order 60 function points for activation. When this is missing on existing relays, that would needs to be enhanced. No problem at all. You can also afterwards order these function points, load it on the device, activates a PQ Basic feature. That's all. Yeah.
Great. Let's just pick a quick one. What kind of information can we provide with PQ Basic, and what can be processed by a substation automation system?
Mhm. Yeah, this is more or less what I showed just now here in the live demo. We can pick up the warning start itself. Yeah, this means that it was detected. Yeah. The overall operation from the tip start with the tip end, event start, event end. The limit violation of each single phase. Yeah. The extreme value per phase, the extreme value overall. The warning off, this means the complete duration of the event. And last but not least, very important, the counter of this event. To make it now visible or clear that over the time range of quarter year, we have fetched on this feeder 5 bits or 1 bit for just statistical purposes.
Thanks. I think let's take one last one, or maybe 2 more. Let's see. But one thing that's probably most relevant in this context is, can I measure and evaluate the feeder in compliance with the power quality grid code EN50160?
Yeah, you can monitor your feeder based on the events, which are also in the EN60160 and THT and TDD. However, there have been some restrictions because the protection relay measures a harmonic up to the 20s. Yeah? But for EN50160, for this complete grid code, we need to measure or to calculate the THT up to the harmonic number 40. Yeah? And also the main signaling or the long-term figure of fundamental content of the EN50160. These characteristics cannot be measured by a PQ Basic functionality protection relay.
So you need a dedicated.
Exactly. When you have the requirement to have a full EN50160, SICAM Q100, SICAM Q200 PQ recorders in our portfolio doing excellent this job.
Okay.
They are designed for that. No?
All right.
Haben wir das Bild? Haben wir das Bild?
Oh, weiter.
Okay. I think we are back live up there.
Back.
Cool. Not entirely sure.
All right.
But well, the auditorium, thank you very much for your attention and especially your great questions. As mentioned, every question that is still not answered will be answered in bulk and provided as a separate PDF file, which you will find somewhere up there again as well. So that means that every question posted during this webinar will be made available for you to browse again. One more hint, the entire Power Quality Basic functionality, as well as the description of the available parameters, is part of every Cyprotec 5 manual as a separate chapter, as already mentioned, somewhere around chapter 11, but it's bold and dash, you will find it. You don't have to look for it anyway. So furthermore, thank you again, Marcus, for your presentation, for your answers during this quick Q&A. I mean, it's live again, just be reminded about that. But before we send you on your way, dear auditorium, please remember to provide us with your feedback. Maybe leave out the technical issues because
sure.
And there should be, again, up there, a new widget where you can give us a bit of feedback. They will also find the slides of this webinar, even if you do not leave any feedback, but still, it will be great.
All right.
The recording of the session will be made available on demand. You can access the recording via the link you already used to join this session. to rewatch the webinar straight away. It's basically already there. Additionally, you will receive a separate email with a quick link to the recording and the questions, as we already mentioned. It was a great pleasure to guide you through the session. Thank you once again for joining. Have a great day. Take care. See you soon. Bye-bye.